All right, this is Unit 1, Lesson 1 for Algebra 1 on operations on real numbers. Okay, so operations on real numbers, our lesson essential question is how can you classify the results of operations on real numbers? At the end of this lesson, you'll be able to reason about operations on real numbers. All right, so example 1. In the set of numbers from 1 to 10, which elements are in both the subset of even numbers and the subset of multiples of 5? So we want to remember that a set is a collection of objects such as numbers. An element of that set is an object that is in the set. We can write a set by listing the elements enclosed in curly braces. So they're the ones that go like that, okay? So in this case, we're talking about the set of numbers from 1 through 10. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. B, we can let B be a subset of set A. So if each element of B is also an element in A, then it's considered a subset. So in this case, our B, we said were even numbers. So in between 1 and 10, our even numbers are 2, 4, 6, 8, and 10. Okay, so those are elements of A that are even. And so that would now be a subset of A, which is now B. Okay. The second subset that we wanted was multiples of 5. So multiples of 5 would be 5, then 10. Okay. So we're going to say that that's subset C. You can choose any letter that you want for the sets unless they specifically tell you otherwise, but they're all denoted by capital letters. So the number 10 is the only number that is an element of both subsets. That's what they actually originally asked me for. So which elements are in both the subset of even numbers and the subset of multiples of 5? So we had to create those subsets, and then we had to find what was in common. All right, so let's try it. Which numbers in set A equal, where set A is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the numbers from 1 to 10. Are elements in both the subset of odd numbers and the subset of multiples of 3. So the first thing we want to do is actually create two subsets. So the first subset we're going to call B. So B is going to be my odd numbers. My odd numbers are 1, 3, 5, 7, and 9. Okay. Then I want to create a subset with multiples of 3. So in this case, my multiples of 3 are 3, 6, and 9. The only one that both of these have in common is 3 and 9. So 3 and 9 would be in both subsets. All right, so let's compare and order real numbers. So this is example 2. Jim is playing a math game where he needs to put a set of 3 cards in numerical order. His cards show 40 over 11, the square root of 324 over 36, and the square root of 10. Order the cards from least to greatest. So we want to find the decimal approximation for each of these numbers. So 40 divided by 11 is 3.63, where the 6 and 3 are repeating. So it'll be a pattern of 3.63636363. Okay. The square root of 324 divided by 36, I can simplify that. I can take the square root of each of those numbers. So the square root of 324 is going to give me 18, and the square root of 36 is 6. 18 divided by 6 gives me 3. And then the square root of 10 is going to be an irrational number. That means it's a number that doesn't actually repeat. The decimal doesn't repeat, and I can't write it as a fraction. So it's going to be about 3.2, okay? Now I can order these from least to greatest. Remember, least to greatest means smallest to largest. So looking at it on a number line, square root of 324 over 36 is at 3. Square root of 10 is between 3 and 3.6, so that's the next one. And then 40 over 11 is my largest number. So from least to greatest, the order of the cards is the square root of 324 divided by 36, the square root of 10, and 40 over 11. All right, so let's go ahead and try it out. So for 2, I want to order each set of cards from least to greatest, 0.25, the square root of 1 over 9, and 6/25. Okay. So it is very helpful if you actually have a calculator to be able to do this. So 0.25 is great. It's already in decimal form. So if I do this, so here's my calculator, right? I want to do square root of 1 over 9. So I'm going to hit the square root button, which is this button right here. So square root, and then I'm going to do 1. And on this button, I can do fractions over 9. And then I'm going to hit the enter button down here. So it gives me 1 over 3. Well, I want to know that as a decimal. So it already gave me the fraction, which is great, but I actually want to change it to a decimal. So what I'm going to do is I'm actually going to hit the white button at the top, the second button, and then I'm going to hit this fraction button here. You can see at the top that it says F to D, and then back and forth it goes the arrow. That's telling me I can go from a fraction to a decimal or a decimal to a fraction. So I just want to hit, again, I hit the white button, and then I hit the fraction button, and then I hit the enter button down here, and it gives me 0.3 repeating, okay? So now I know what square root of 1/9 was, and now I'm going to do the same thing for 6 over 25. So I do 6, and you can do the fraction button over 25, and that equals, gives you that fraction again. Again, you have to do the second, and the fraction button, and the enter. I get 0.24. You can also use the division button because fractions are the same thing as dividing. So if I have 6 over 25, I can do 6 divided by 25 and I'll get the same answer. So for 0.25 and the square root of 1/9, remember we got the 0.3 repeating, and 6 over 25, we got 0.24. Now we need to put them in order from least to greatest, smallest to largest. So 0.3 repeating is my largest. 6 over 25 is going to be my smallest because that's 0.24. And whatever form they give them in to start with, that's the form that you want to leave them in. So in this case, it's 6 over 25, and then 0.25, and then it's going to be the square root of 1 over 9. So when you're typing these into Savas Realize, you can either use this little calculator button down at the bottom, okay? So that'll pop up, and then you want to go to Basic, and then right here is where you can find a square root symbol. So you just click on that and it pops right in. Then you want to hit the minimize button so that way it's kind of out of your way. You can always go back to it. So I have 1, and then you're going to look for the question mark button on your computer. That gives you a slash, which in Savas is going to automatically give you a fraction. If you don't want to remember that, that's fine. You can go back down here. You can hit the fraction button. Okay. So 1 over 9. So again, smallest to largest. All right, we want to do the same thing for letter B, square root of 121 over 25, 2.25, and the square root of 5. So the square root of 121 over 25 gives us 11 over 5, which equals 2.2. Then I have 2.25. And then I also have the square root. Then I have the square root of 5, and the square root of 5 is going to give me 2.23. So if we're looking at these, again, we want to go from least to greatest, so smallest to largest. My smallest number is going to be the square root of 121 over 25 because that's equal to 2.2. Then I will have square root of 5, which is 2.23, and then I'll have 2.25. So these are a lot closer together if you notice. So I have the square root of 121 over 25, square root of 5, and then 2.25. Check our answer. All right, example 3, operations with rational numbers. A is the sum of 2 rational numbers, always a rational number. So if I add two rational numbers together, are they always going to be a rational number? So you can try several different cases of adding two rational numbers. So 1/2 plus 1/3 gives me 5/6. 7/8 plus 3/4 equals 13/8. 11/5 plus 1/6 equals 71/30, things like that. Okay. In each case, the sum, when I add them together, it's also rational. But you can't try every single pair of rational numbers since there are infinitely many of them. Basically means there are so many we can't actually count or quantify how many there actually are. How can we know for 100% certainty that whether it's true for all rational numbers? So I can use variables to represent any rational number that I want. Okay. So I'm going to let A, B, C, and D are integers. So they're whole numbers. So you're looking at like negative 1 million all the way up to a million. And they continue on forever and ever too. There's an infinitely many integers as well. Okay. So with B not equal to 0 and D not equal to 0. Okay. Because we're going to set them up as rational numbers. All rational numbers can be written as fractions. So I have A over B plus C over D. So when I simplify that or try to add them together, again, B and D are not like denominators, so I need to multiply A over B times D, and I need to multiply C over D times B. What that gives me is AD divided by BD plus BC divided by BD. Okay. Since B can't be 0 and D can't be 0, that also means that B times D can't be 0. Because I can't have 0 in the denominator because you can't divide by 0. Since AD plus BC and BD are integers and BD cannot be 0, the sum has to be rational. So next I want to know, is the product of two rational numbers always a rational number? So I can do something very similar to what I did with the sums. So I'm going to multiply them together. So I want to use the same strategy. So using variables, I'm going to represent my integers. So I still have A, B, C, and D. You don't have to use A, B, C, and D. You can use any integers or any numbers or any variables that you could possibly want or imagine. A, B, C, D is just the easiest way because they're the first four letters in the alphabet. Okay? So I'm doing A over B, because that's my first rational number, times C over D, which is my second rational number. Again, B and D cannot be 0 because you can't divide by 0. When I multiply them together, I get AC over BD. Again, BD can't be 0. When I multiply two numbers together, I can't have 0 in the denominator. Again, since I can't, when I multiply through, I do B times D, which gives me BD. Again, B times D can't be equal to 0 because you can't have a 0 in the denominator. So since AC and BD are integers and BD is not equal to 0, the product of them is also a rational number. All right, so let's try it. I want to know, is the quotient of two rational numbers always a rational number? And then I want to explain. So again, I can use something very similar. We're going to let A, B, C, and D be integers. Okay. So again, I'm dividing. So I have A, B, divided by C over D. Okay, so when I'm dividing by fractions, I'm going to actually end up multiplying by the reciprocal. So this is the same thing as saying A over B times D over C, where A, B, C, and D are not equal to 0. So this gives me AD over BC, where B times C does not equal 0. So yes, the quotient is always a rational number. We have a little bit more of a restriction on it. We have to say A or B, D, and C can't be 0 because, again, we're dividing by those numbers. or you're multiplying through. So if C were a 0, for instance, and I go to divide those fractions, then I'm dividing by 0 and I can't do that. Okay.
Is the sum of a rational number and an irrational number a rational or irrational number? Write the sum of an irrational number and a rational number as a rational number. Every rational number can be written as an integer divided by a non-zero integer. So for a divided by b and p divided by q to be rational, a, b, p, and q are integers with b and q not equal to 0. Solve the equation for c. First, subtract a divided by b from both sides of the equation. The equation becomes c equals p divided by q minus a divided by b. Write the right side of the equation with a common denominator. The equation becomes c equals p times b minus a times q divided by b times q. In the equation, the numerator is an integer because it is a combination of integers by multiplication and subtraction. So p times b minus a times q is an integer, and b times q is an integer not equal to 0. Therefore, p times b minus a times q divided by b times q is a rational number. This is equal to c. But from the given statement, c is an irrational number. But this is a false statement. A number cannot be both rational and irrational. So what went wrong? The mistake was to assume that you could write the sum a divided by b plus c in the form p divided by q in the first place. Therefore, the other choice, the sum must be irrational, had to be true. The sum of a rational number and an irrational number is always an irrational number. Is the product of a rational number and an irrational number rational or irrational? Write the product of a rational number and an irrational number as a rational number. By definition of a rational number, a, b, p, and q are integers, with b and q not equal to 0. Solve the equation for c. Multiply both sides of the equation by the reciprocal of a divided by b, or b divided by a. Since a times b times a equals 1, the equation simplifies to c equals p divided by q times b divided by a, or p times b divided by q times a. P, B, Q, and A are integers. The product of two integers is an integer. So P times B is an integer and Q times A is an integer. Because P times B is an integer and Q times A is an integer, C is the ratio of two integers. So C is a rational number. Since we started with C as an irrational number, now C is both rational and irrational. So the assumption that you can write a divided by b times c as p divided by q at all is wrong. When you multiplied both sides of the equation by the reciprocal of a divided by b, you were dividing both sides by a and 1 divided by b. Also notice that in order to divide by a when calculating c, you have to assume that a is not equal to 0. If a equals 0, then a divided by b equals 0, and a divided by b times c equals 0 for any number c. So the product of a rational number and an irrational number is always irrational, unless the rational number in the product is 0.
All right, let's go ahead and try it. So try problem number 4. Is the difference of a rational number and an irrational number always irrational? Explain. So again, we can use some of the same logic that we've used for addition or the sum and product of a rational and an irrational number. So in this case, all right, try problem for number 4. Is the difference of a rational number and an irrational number always irrational? Explain. So you're going to use something very similar to what we've done to find the sum and the product of rational versus irrational numbers. So I'm going to start with a number that I'm going to say is irrational. So let's say m is my irrational number. So I have a over b. So again, I'm taking the difference between a rational and an irrational. So a over b minus m. So a over b is my rational number. M is my irrational number. This is going to equal, because of course I can't just subtract them. So I need to multiply the m by b over b. So I can come up with a number that works and I can subtract them. So this gives me a minus mb over b. And we already said previously that when I added a rational and an irrational number together, they were an irrational number. So this is already an irrational number to begin with. So since m cannot be written as the ratio of two integers, a minus bm also cannot be written as the ratio of two integers. So all in all, my answer is yes. Difference between a rational number and an irrational number is always irrational. Okay, concept summary. So my concept summary for operations on real numbers in words: the sum of two rational numbers is always rational. The product of two rational numbers is always rational. The sum of a rational number and an irrational number is always irrational. The product of a non-zero rational number and an irrational number is always irrational as well. Okay. So we can see these in numbers, both sum and product with rational versus irrationals. And we can see it in algebra with the variables that we use. And that is the end of Unit 1, Lesson 1.